sense. Peter, in terms of detectors, he wrote the book on it, literally. So it's a real pleasure to have him here to describe it. Peter has a real broad outlook on gravitational wave physics. In addition to knowing everything, in describing everything there is to know about the detectors, he really brought issues like thermal noise to the forefront when the detectors are being designed, addressed issues like what does it mean to try and detect the gravitational wave strain with one of these detectors when the gravitational wave is going to be acting on the photon as well, or issues related to the history of physics and history of gravitational wave detection. So it's a real pleasure for us to have you here, Peter, to
Great.
tell us about the detectors.
Thank you so much, Nelson, and I'd like to thank all the organizers for the opportunity to be here this week with you all. It's a tremendous honor and pleasure, and I hope we have fun learning together. I'm already learning from you all as well. Before I start my prepared talk, let me do one or two things. First of all, just for my benefit, do an informal poll. Could I ask you to raise your hands if you consider yourself an experimentalist, more or less? Okay. A theorist, more or less? Okay. How about neither? There may be some people in okay. That's very interesting for me, and I'll talk to the neithers later. I can imagine what you all might mean, but I'd actually like to know. So let me say a bit about what I hope to do with the 5 lectures for this week and one next week. I've got a few goals, and I've put them up here on the screen. One of them is to make sure that there's no one who leaves this summer school who does not understand that gravitational waves aren't just solutions of the Einstein equations, but things that we can actually feel, which is to say measure them. That's idea number one. That's really important for me to convey. Not that anyone ever conveys the opposite, but somehow, maybe sometimes it doesn't feel like that's the most important thing. So they can be felt in principle. They can be measured in principle. However, the gravitational waves that nature presents to us are so weak that detecting them is almost impossible. And I mean that in the most literal sense. I will be spending a lot of time trying to convince you all how hard it has been, so that no one is in danger of taking for granted the fact that here we are close to 3 years after the first detection, and okay, it's part of astronomy, it's wonderful, it's great, and that's all true. But it almost didn't happen, and 3 years ago we didn't know if we would ever succeed, for good reasons. Okay, so it's a great gift, and we want to understand both how it turns out that nature provides us with such weak waves that it's almost impossible, and how, nevertheless, the impossible has been made possible by decades of hard work. And the senior people who are with us today have been parts of that team, really important ones, making tremendous strides in manipulation of light and creation of precision optics, in pushing mechanics into regions it had never gone before, and in applying non-equilibrium thermodynamics to material science in ways that no one had thought was necessary before, and finally, if we have time, through innovations in electromechanical control. And it's my belief that even theorists can and should understand these issues. And so I would like to express strongly to you all my belief that I love seeing raised hands and questions. I've prepared material. I could talk all day about this, but I would much rather talk about less and convey more. So please don't be shy. Please ask questions about this material as we go. So with that as a ground rule, let me say a bit about what I have put together for part 1. And if we don't get through part 1 before it's time at 7 o'clock to leave and party, that's fine. We'll pick up with it tomorrow. So my goals for part 1, however long that takes, are to, in my own language, the language I think that's best suited to understanding the experimental aspects of this field, understand what gravitational waves are and why we know they must exist because of what we understand about relativity. And then with that as a foundation, understanding gravitational waves more vividly in terms of which it becomes obvious that they can, at least in principle, be measured. And that discussion of the in-principle measurements will go on to how, in particular, interferometers, the technology that finally achieved the sensitivity necessary to find them, how interferometers work and how they interact with a gravitational wave so that the gravitational wave can, in principle, be measured. And if we have time today, and if not, we can do it another time, I have some words about something that might be called the rubber ruler puzzle that Nelson mentioned, this question of once you start thinking, okay, gravitational waves move mirrors, they stretch light, doesn't that cancel? Okay. How I convinced myself some years before the discovery that we hadn't made a gigantic mistake. And
very many smart people have recently said, oh no, it just can't work.
well, okay, we have to understand it. Yes, that's fine. But it's part of our responsibility to understand why that's the case. All right, so that's where we're going to go. And now let me remind you of what I think is the most cogent argument that says gravitational waves must exist. I'll take as one of the key results of relativity, I heard it was not a postulate but a result this morning from Tom, that no signals can travel faster than light. And now let's apply that idea to at least a naive understanding of Newtonian gravity. Naive in the sense that what I'll assert is that I believe momentarily Newton's law of gravitation exactly and precisely to mean that if I have two objects, mass 1 and mass 2, separated by a distance r, there's a force between them given by F equals gmm over r squared, pointed along the vector that connects them. And if I take that naively and literally, if I should move one of those masses to the side, along the vector that connects them, whatever, Newton tells me in my naive frame of mind that instantaneously the other mass should feel a different force. So at that level of naive understanding, gravity sounds like it violates the principle of relativity. But I believe in relativity. I don't think that can be. Therefore, I believe that there must be some richer phenomenon in gravitation that performs the function of propagating the news that one mass moved only at the speed of light, and that phenomenon of propagating the news at the speed of light is what a gravitational wave is and ought to be. So I think it's a pretty straightforward argument. Now, here's another quick poll. Raise your hand if you have seen this diagram ever before in your learning about electromagnetism. All right, I'm glad to see some hands, but I'm performing a public service. By the time you leave, everyone in this room will have seen this diagram. So this is an application of that kind of thinking, plus some mathematics as well, to the equivalent argument that electromagnetic waves must exist if relativity is true. It must be the case that Coulomb's law is not the whole story for the electric field generated by a charge. So let's walk through this diagram. So right there is the instantaneous location of a charged particle. There are field lines connected to that, pointing outward, because we're talking about a positive charge. But you'll note that that field configuration doesn't look like the diagrams that are usually drawn in the first section of the chapter of your textbook on the electric field, and that's because the charge used to be sitting right there, and then a few moments ago, it was suddenly accelerated into a rightward going constant velocity and kind of fast motion. And what we're looking at is the configuration of the electric field a short time after that charge ceased to be sitting still at its original position and started moving off to the right. And what the diagram, first drawn to illustrate this idea by J.J. Thomson, what it illustrates is that far away from the charge, the field still is radial from the original position. Near the charge, the field is radial about its current position. And we have a kink in the electric field lines that is propagating out at the speed of light that performs the function of changing the field from its original direction and strength to its appropriate direction and strength for the position and state of motion of the charge. And you'll notice this must be a relativistic velocity because the field lines are much closer together here than here. That's what you expect for a charge moving at a high velocity. So these kinks are transverse electric fields, and they are in fact the electric component of the electromagnetic wave propagating out at the speed of light. And I'm doing this just diagrammatically to make sure everyone has seen this idea, but Thomson actually made sure that you could do everything, that you could get the strength of the wave, of the field in the wave correctly as well. So we know this argument works for the electric field. And I want to assert that just by logic alone, logic and relativity, there ought to be an equivalent for gravitational effects. Now, gravitation, as we heard at some length this morning, is not a vector, so you can't draw a diagram quite this simple, but the basic idea is there, and at least at the rough level, the analogies work. So I want to use some more analogous thinking from electromagnetism to motivate a few more things about gravitational waves. So I want us to think about a thought experiment where I'm going to have a grid, a 9 by 9 grid of charged test particles. And let's imagine that the charges are small enough and they're far enough apart that we don't have to think about the Coulomb repulsion among those particles. And let's just make our apparatus be this grid of particles and ask what's going to happen to it when an interesting influence happens. In particular, the interesting influence I want you to think of is an electromagnetic wave propagating from the back of the room through the screen. And let's imagine that I'll specify in particular that electromagnetic wave has its electric vector oriented in the vertical direction. So how ought the locations of these test particles, these test charges, move in response to an electromagnetic wave with vertical polarization propagating through the plane of the screen? What should it be? Oscillating up and down. Great. Everyone knew that, right? Y'all were just too shy. That's right. That's right. And in fact, this is the dominant effect. And sure enough, now I've drawn empty squares where the charged particles used to be, and at some particular phase of the motion in response to the oscillating wave, all those charged particles have moved up. That's how we recognize that we're dealing with a vector effect in an electromagnetic wave. The electric vector is pushing all those charges upward. And this is why, if you have a radio, it has an antenna. That's a wire, so that the electric part of the electromagnetic wave from the radio station can move all the free charges in the metal along the wire, producing a current that then the rest of the radio amplifies, demodulates, and presents to the speakers so that you can hear the music on the station. Okay. So this is all familiar physics to everyone. Now, let's start pushing the analogy back to gravitation. So I want to set up a new experiment with a new 9 by 9 grid of test particles. But this time, I don't want them to be charged, at least not electrically charged. I want them with the gravitational charge, which is just mass, after all. So these are all free to move. They have the gravitational charge, but nothing else. And now, instead of sending an electromagnetic wave through the previous apparatus, I'm going to say, let's imagine we've got a gravitational wave propagating from the back of the lecture hall through the plane of the screen. And here is the response. I'm just going to assert the response for a particular polarization of the gravitational wave. And now, is this the same geometric pattern of response or different? It's different, all right? It's got a very different symmetry. Instead of all of the test particles shifting in one direction, there is a quadrupolar pattern. From here to here, we change sign, change back again, change back. That's a quadrupolar pattern. It's also interesting in that I haven't drawn squares that have moved the same distance from their original location as each other. Instead, what we've got is a fractional change in the positions of the particles. Everyone has moved not by a certain amount, but with respect to this center one, by a certain fraction of the separation from that central one. Yes? Mm-hmm. Mm-hmm. Uh-huh. Yeah. Mm-hmm. Yes. Mm-hmm. Would be vector-ish. Well, do remember, though, that there's only one sign of gravitational charge. So if I tried to do this with gravity, I would have to have another gravitational charge move to the left to conserve momentum. And I think that's now part of the story, and maybe Tom wants to jump in and save me some more, but I think people have always understood the difference between having one charge and two. And great, so you've saved me by saying wait until a future lecture. Yeah, okay, so nice question, it's interesting. Yes, Eric. Great, okay, thanks all. Yes. Mm-hmm. Right. all has the ring of truth, and the only thing I don't know is how early or late in the history that we were being asked about that was understood. All right, so this is an important pattern for us to keep in mind, the quadrupolar pattern, the fractional stretching character that I will sometimes call a strain. So it's a quadrupolar strain in space. Something else I would like you to recognize, and that is you've already seen a diagram that is strikingly like this already this morning. Here is a diagram that I am borrowing with my thanks from Tom's talk this morning about how you can recognize a gravitational field acting on a set of test particles. And he said, let's imagine that my apparatus is a set of 4 freely falling test particles in a box so that I can't see outside and I can only make measurements with these test particles. And I can think of this apparatus in 2 different cases. One, just floating far from any gravitational affecting mass, and one close to a planet. And what we saw this morning was that by virtue of what we understand from our Newtonian intuition about how gravitation is not uniform but is pointing towards, in this case, the center of the Earth, we expect this quadrupolar distortion in our pattern of test masses. The ones side by side will come together, the ones up and down will stretch apart, so it's got the same kind of orientation that this pattern has. Now, in this case, if we want to imagine that we are using this apparatus to detect gravitational effects, something that is implicit in setting this up is that we're going to be able to recognize this by measuring the separations between these test particles with respect to a framework of rigid rods. That will come back as an interesting idea in not many slides from now, but I did want to point that out. If you're imagining you're going to do experiments the way we normally like to think about experiments, and inside a small box, we can do it. We can detect gravitation by this kind of thing in a box, and we do it by measuring with respect to a rigid coordinate system defined by rigid rods. Now, I don't want to overstate the analogy between gravitational waves and this manifestation of gravity. For one thing, gravitational waves are not a steady DC effect. They are, at least usually, often oscillatory. And here I've got a version of that apparatus where instead of having a 9x9 grid or 4 particles, here I've got 8 particles, but you can see the analogy. And now, as the gravitational wave is propagating from the back of the room to the front, what we would notice, as long as we had the right kind of measuring apparatus, and it has to be the right kind in principle, and it has to be of sufficient sensitivity, this gravitational wave wouldn't be too hard to detect. This is a pretty strong one. This would be the sign that a gravitational wave was propagating through our apparatus. This kind of quadrupolar change in separation between neighboring particles, and that it's time dependent as well. Okay, so that's what we're going to look for. And now let me just introduce some terminology that's all over our field. If I characterize the difference from the original positions of particles in my apparatus, if I characterize it by the fractional separation change between any pair, and it doesn't matter which pair I pick, I get the same value. That's what I'll call delta L over L. We normally talk about the strain amplitude as a number that turns out to be twice the fractional separation change. And at an appropriate moment, I think I'll be able to make that clear where that factor of 2 comes from. But what's more important than remembering the factor of 2 is when I keep talking about the strain H, this is what I'm talking about, the up to this factor of 2 fractional change in separations of particles. Okay, so that's the breezy introduction to the field, and it should be obvious that gravitational waves ought to exist, maybe not quite so obvious that they have this pattern, but that they exist should be real. And now I want to inject a note of historical irony, and it's really kind of profound. The prediction of gravitational waves was made by Einstein within a year of his first publication of his thoughts about general relativity. Published this idea first in 1916. But then, more or less for the rest of his life, he oscillated between belief that they were a real physical effect and belief that they were a mathematical artifact that could be transformed away by finding the right coordinate system. And as far as I know, he went to his grave in 1956 not really being sure of the answer. So maybe we shouldn't think that kind of argument that in one slide I could make it obvious is so obvious if Einstein himself doubted it. But it's worth.
Can I just make a comment? So
Please.
I'm sure you're aware of this Daniel Kennefick's book about
Yes.
history.
Yes.
I think he tells a story about this. Was it Robertson and Caltech helping him with this paper?
Yes.
Surreptitiously about cylindrical gravitational waves, which Einstein and his compatriot finally got right with Robertson's help.
Right.
So did he think that was just unphysical or something?
Well, all right. The particular episode. Let me just fill in. You're telling it really well, but I'll just fill in one or two other facts that I remember about it. So Einstein, and I think it was Infeld, who was his co-author, sent a paper to the Physical Review claiming to be able to show that they could transform away with an appropriate transformation all the manifestations of a particular gravitational wave solution, and their conclusion was, therefore we have shown that gravitational waves aren't a physical effect. And you're absolutely right. The anonymous referee, who we know with historical hindsight was Robertson, communicated to Einstein. He was incensed that anyone would dare to review a paper of his, okay? That was not the European tradition that he was used to, I guess. Withdrew the paper in a snit, then thought about it some more and realized that the anonymous referee had been correct, and then he and Infeld published another version under the same title but with the entirely opposite conclusions in another journal. But even though that's true, I'm not sure that that proves that Einstein then was converted, only that he realized that this particular calculation that he'd done had been incorrect. But that was, I think, 20 years after this. Now, maybe, in the last years of his life he was really convinced, but I haven't heard any evidence to that effect. What we do know is that his doubts were widely shared. If you look at Eddington's early textbook, and I wrote early because I don't remember the year that this came out, textbook on relativity, you will find the remark that Eddington says, some people think that gravitational waves travel at the speed of thought, by which he meant that they weren't physical, that they were things that you could imagine transforming away. He phrases it in such a way that it doesn't seem that Eddington is actually endorsing the point of view in this quip, but it was out there. Something that makes me think that Einstein worried about this for the rest of his life is that I've been struck by the fact that Einstein was really good at inventing thought experiments, and not just the three classic ones. If you read some others of his papers from later on, you'll see, for example, the dragging of inertial frames by rotating masses that was only verified in the past few years by the Gravity Probe B satellite, was proposed by Einstein in a public bit of writing. But I have never seen anything where Einstein says, and you know what, there's this really interesting effect that I propose that would be a great thing for an experiment to do, namely gravitational waves. Okay. So I find that striking. Now, only a year after Einstein passed away, the controversy ended. And we know the precise week and the precise location when the community of relativists collapsed into uniform belief in the existence of gravitational waves. And it happened at the Chapel Hill Conference in January of 1957. And the person who forced this collapse of the wave function was Felix Pirani, a really great relativist about whom he's too few people's hero, but he's my hero, mainly for the talk that he gave at Chapel Hill that convinced everyone that gravitational waves were real. And he did it because he was able to get out of a particular rut in which a lot of other smart people were stuck. Namely, most people who were working on the problem thought that they ought to think of a source of gravitational waves and work out the dynamics of that source. And I'm miming a binary system. That was one that people were studying. And show that those motions caused this kind of gravitational wave that you couldn't transform away. And it's a really hard problem, right? And even after the effect of gravitational waves on a binary system was demonstrated by Hulse and Taylor, there was still a very learned dispute in the relativity community about, should it be obeying the quadrupolar formula or not? It's a really hard way to do the problem. What Pirani did was say, let's imagine that there are gravitational waves, propose a kind of detector that we can show receives an effect that can't possibly be transformed away, and therefore will show that gravitational waves must have physical reality. So he switched from the source problem to the detector problem. Now, one wonderful thing about that conference was that you can read the entire transcript of the meeting, not just the talks that were given, but also the question and answer sessions. And I used to think that you needed to find a very obscure mimeograph copy from 1957 of the proceedings, and that's the one I first studied. But in fact, there's an online copy of the entire proceedings. I'll give the URL in a bit, I think. No, I won't. But I will give the URL to anyone who asks me. So anyone is capable of reading both Pirani's talk and what's almost as cool, the question he got from Hermann Bondi, his senior colleague, right afterwards. So here is a part of Pirani's talk. And what I want to do, I want to make sure, because I know that's small type. Okay. Can people in the back row see that now? Okay, this is the equation of geodesic deviation. And we saw this morning. And what Pirani is saying is, okay, I know how to calculate the Riemann tensor for a plane gravitational wave. And let's imagine I have two neighboring test particles. Let's make them close enough so that we don't think there's any subtlety about measuring their separation. A gravitational wave goes by that pair of particles. They will move with respect to one another. They will move in a way that's unambiguous, that no matter how you think you ought to invent the apparatus, that you could measure with respect to a rigid ruler attached to one or whatever. So he says, you know what? We've had this equation of geodesic deviation floating around, and it always contained the answer to this problem. In fact, he goes on to say, let's see if we can, whoops. Maybe I can have you read this or not. By measurements of the relative accelerations of several different bodies, one may obtain full details about the Riemann tensor. One can imagine an experiment for measuring the physical components of, what's the word? Of the tensor. And people immediately went nuts. They said, this is it. This has given us, in fact, if you read the conference summary talk by Peter Bergman, he says, one of the most important things that happened this week is what we learned from Pirani, that now we know how to design any experiment we want that will reveal all the physical aspects of gravitation. We'll just imagine setting up the appropriate set of test particles and measure their relative motions, and we're done. This is a great breakthrough. You can read it right there. So that's pretty fabulous. Okay. Now, here's the thing that I really think we ought to thank the DeWitts. Okay. This conference was organized by Bryce and Cecile DeWitt, and we are here at Les Ouches, founded by Cecile DeWitt, right? So we have to thank them not only for this wonderful place, but for producing a proceedings volume that recorded this wonderful exchange between Hermann Bondi, who was a senior colleague and mentor to Pirani, and Pirani himself. And here's the bizarre twist in this story. They must have had offices just right down the hall from each other. They flew on the same airplane from London to Chapel Hill, North Carolina, to this meeting, but they only have this discussion in front of 44 of the world's leading relativists live, unless this was staged. I don't know, maybe it was staged. But Pirani raises his hand after Bondi raises his hand after Pirani's talk and says, "Do you mean that I could attach a dashpot between two test particles and see that it absorbed energy and warmed up? Is that what you're saying?" And Pirani wrote, and this Pirani says, this is fabulous. "I've not put in an absorption term, but I have put in a spring. You could invent a system with a term quite easily." Okay, like, come on, of course, that's what I said, right? But he said it a little more politely to his senior colleague and mentor. Now, as Dan Kennefic's book goes on to show, Bondi got credit for solving the gravity wave problem by showing that you could warm up a dashpot. And I think Bondi kind of liked that. I'm really not sure of how that history all played out, but the proceedings volume tells you quite clearly that all the interesting thinking came from Pirani first. So that was the moment. I haven't figured out from the transcript exactly which day in the week this talk happened, but plus or minus a couple of days, we know exactly when Einstein's doubts were resolved. We know more than that, though. Not only was this the moment when all theoretical doubt about the existence of gravitational waves ended, it was precisely the moment when the quest to detect gravitational waves began. And we know that because Joseph Weber was at the meeting, and he gave a talk earlier in the week about his attempts to think of how you could invent a gravitational wave detector, and it was kind of a crummy talk, and Bondi raised his hand afterwards, and you can read this in the proceeding. He says, "You know, Weber, I think you ought to go down a different path. You're never going to get an answer the way you're going." Okay, so we know Bondi was, would say what he thought to anyone. And so he put down Weber. He helped out Pirani clarify his point. So we know Weber was there with his mentor, John Wheeler, from Princeton. And we also know, and this I've got in part by private communication from my colleague at Syracuse, Josh Goldberg, who was at this time working for the United States Air Force, funding gravitational wave research, not only in the United States, but also in Europe. And Josh was the person who wrote the check for funding the meeting, for bringing Pirani and Bondi from London, and about a half a dozen other folks from Europe. And Josh tells me that Weber told him on the way out the door at the end of the week saying, "I'm working on gravitational waves. I'm fired up for what I learned from Pirani, and you'll be hearing more about what I've done soon." And separate from that, there is, in fact, a paper in the Physical Review sent in not many weeks later that does two things. It summarizes Pirani's argument and gives credit to both this exact talk and the published paper that Pirani had sent to the journal several weeks before the conference, and then goes on to give the first not quite recognizable version of what became Weber's idea for developing gravitational wave detectors just a few weeks later. And then if you comb through what you can easily find online, you will find that Joe sent in prize-winning essays to the Gravitation Research Foundation essay contest, both in 1958 and in 1959. The 59 one is better than the 58 one. 58 won third prize, first prize in 1959. And by this time, this essay was basically published without much change in the Physical Review in 1960. This is Weber saying, here is how you can go out and detect gravitational waves with resonant massive objects. I'll explain more for those of you who don't know that story, but we can trace a direct line from Pirani's talk to the start of the gravitational wave detection program, and I will make even another historical link to that talk in a little while later. But I don't know of any historical episode where the catalyzing moment of 50 years of effort is so easily documented. So I'm really charmed that we have this kind of information. So here is what came to be known as a Weber bar, a resonant detector for gravitational waves. This is a thought experiment version. I'll show you a photograph of a real one in just a moment. Weber's basic idea was to make some massive object, several tons of aluminum, a cylinder, a meter or two in length, pretty fat as well. And he said, we can think of that massive object as actually consisting of two test particles. They're rather big test particles, the two ends of the bar, connected by the material in the middle, thought of as a spring. This is a freshman version, a first-year physics version of what a second-year physics student would say is the fundamental longitudinal normal mode of that resonant cylinder, but to connect it to Pirani's thinking, I like to think of the different parts of the bar playing these different roles. And the idea is that if a gravitational wave propagates through this detector, there will be a tendency for the two ends to be pulled apart, be pressed together. Now, these aren't free objects anymore. They're connected to the spring, so the dynamics that the spring adds is important, but it doesn't make it so that it doesn't see anything. It's what it does guarantee is that the stiffness of the spring will prevent measuring low frequency gravitational waves. The spring will press back and forth, but for fast enough gravitational waves, this will respond just fine. And in particular, Weber pointed out that if the gravitational waves actually oscillate at the frequency of resonance of the system, you actually will get an enhanced response beyond a Pirani-style free detector. So, sounds kind of cool. And here's a photograph of Joe, not in the 50s. This is probably in the very late 60s or early 1970s, working on one of his bar detectors. And I love this picture. So first of all, you can see it's a big cylinder of aluminum. You can see it's, somewhat more than a meter long. You can almost see the smoke rising from the solder as he's attaching leads to those piezoelectric strain detectors, which sought to see that the bar was being stretched and compressed by seeing that the material around the midline, the part that's the spring, is undergoing an oscillating strain. So we've got test mass there, spring, and sensors in the spring part that are absorbing through their electromechanical effect energy from the oscillation of the cylinder and sending it to the input ports of an electrical amplifier. So not only can you think of them as the sensor part, which they are, but they're also Bondi's dashpots, playing the role of taking energy that was deposited in the bar by the gravitational wave and sending it someplace else where you can see that that energy showed up.
You know, that bar looks like there's a dark wire. Do you know if it was a suspended bar?
This, you mean this one? Oh yeah, that is the suspension. Okay, so let's say a bit more. Weber not only invented the first gravitational wave detector period, but pioneered many of the technologies that proved to be so valuable that we use them over and over. So this is, I'm guessing a steel cable that wraps around and is grabbed over there, that suspends the bar so that it's only very lightly connected to the outside world, and suspends it from this arch which is sitting on sets of alternating layers of lead bricks and rubber sheets. That is a mechanical vibration isolator. The floor is shaking a lot. We'll have a lot to talk about that later in the week. But in order for it to disturb the bar, it has to not only move, but it has to stretch some of that rubber, and that only through the stretching of the rubber and the rubber's spring constant does that move the first lead brick, and then there's another rubber sheet, and so on, a chain of harmonic oscillators, which have the property that for frequencies high compared with the resonant frequencies, they move very little. So Weber invented the conceptual apparatus and a lot of the stuff that was necessary to make it work. What you don't see here, obviously, because Joe is soldering, is you don't see that this whole apparatus was put inside a vacuum chamber so that sound waves didn't disturb it. He worried a lot about electric and magnetic isolation to make sure that there was as little external disturbance as possible. That's because gravitational waves are weak and you need to be looking for pretty small effects. So thanks for that, for getting me to point that out. Thanks, that was great. Okay, now, what followed was kind of a soap opera. It was a drama with all sorts of emotion attached to it. In 1957, Weber starts this program. By 1969, he was working pretty hard, okay, 12 years. He wrote the first of a number of papers in which he announced that two of his detectors, separated by quite large distances, showed a statistically unbelievable number of coincident excitations unless they were subject to the same external influence. And although Joe at some points of his life denied that he ever said in so many words that he was detecting gravitational waves, the papers were written so that everyone who read them to be saying that I, Joseph Weber, have detected gravitational waves through a number of brief impulsive events exciting widely spatially separated detectors into oscillation. There's another innovation of Weber's, that this was a delicate enough thing that you need multiple detectors separated by great distances, and we could go on. So this would have been the most amazing discovery in 20th century physics, not least because it didn't take some physicists long to realize that if something as insensitive as Weber's apparatus was detecting impulses strong enough to be seen, and that frequently, that a substantial fraction of the Milky Way was being turned into gravitational wave energy in the course of a Hubble time. So this was actually, there was reason to be suspicious. Yes? Yeah, but not ultra high frequencies. The resonant frequencies were around a kilohertz. So that would have missed our black hole signals so far, but the neutron star signal swept through that frequency. So it was far from a ridiculous frequency, but the sensitivity was mostly in a narrow band that Now with hindsight, we realize, maybe could have been chosen better, but that wasn't, well, that was one thing that with the benefit of hindsight we see was a weakness. The bigger or more obvious one was how big a motion of the ends of the bars would have been required to be seen above all the other noise, including the electronic noise in the amplifier. And the answer is that something like a strain of 10 to the minus 15 was what Weber could have seen. We now know that's just 6 orders of magnitude in amplitude or 12 orders of magnitude in power. Inadequate. So with the benefit of hindsight, we understand things that in the moment were hard to understand. But let's turn it around. It would have been amazing if it were true. Yes.
Was then understood what he was measuring?
I'm sorry?
I mean, he claimed to measure very
Yes.
different ways,
Mhm.
but then did people understood?
Eventually understand. I have never heard any explanation of, oh, yes, it was crosstalk between these 2 wires when he brought the signals together. I have my own theory, and it is not a theory of a physical problem. Let's leave it at that.
Do you know that he invited groups to check out?
Yes, yes, he did. Yes.
That was the polite thing to do.
It was the polite thing to do, but I've talked to some of the people who visited his lab, and they, to a person, say, I didn't get the answers to all the questions that I wanted. It was the weirdest lab visit I've ever had. Yes? There sure were very soon afterwards, and good people too. I mean, blue chip physicists. There's a really interesting review that came out in the early 70s by Kip Thorne and Bill Press that walks through a huge range of possibilities, and it's a review article because there were plenty of papers within a year or two that examined this, and that's when people realized, these seem kind of strong, even if the sources are as close as the center of the Milky Way. And that's one thing I didn't mention. Weber said that there was a time dependence to when he saw extra coincident pulses and when he didn't, that was consistent with the idea that the center of the Milky Way galaxy was the source. So that's what people focused on, and the numbers weren't working out. Yes?
So people were expecting a signal of around 10 to the minus 15?
No, none of those of the results that Thorne and Press reviewed actually said, okay, it could be this.
But is that the strain that he was claiming? Because I didn't understand this number.
Yeah, all right. You will not find Joe's strain sensitivity written in clear language in any of his papers. That was partly why people had to visit his lab to try to understand what it was. What was the calibration of his apparatus? Yes?
So they are cryogenically cooled?
No, these were room temperature at the time.
No, okay, yeah, I know.
Okay.
These are in development, right? There are projects actually.
Well, cryogenic bars ran in the 1980s. Okay.
I'm just
Yeah.
wondering if there is anything in development that picks up this idea and pushes it forward to.
I will answer your question in a moment. It's the right question. Okay, so the beginning of the answer is at the bottom of this slide. Namely, as soon as this announcement came out and people saw how simple Weber's apparatus was, a lot of people around the world, also blue chip physicists, said, okay, within a year, I and a few of my buddies, we can build a gravity wave detector too. So, University of Glasgow, Rome, Frascati, Munich, Bell Labs, IBM, and I think I'm leaving out a few others as well, but these were the leading groups, immediately said, well, let's confirm. I don't think they necessarily went in to refute. They said, this sounds great, let's do it. And here are some of the heroes of this episode. Ron Drever, who also played an essential role in LIGO, as did his junior colleague Jim Huff. Eduardo Amaldi, they were both in Glasgow. Eduardo Amaldi founded a group in Rome. Richard Garwin, a very famous American physicist for many reasons, built a small detector at IBM Labs. Tony Tyson, who's done fabulous work in astronomy, built a detector at Bell Labs. And here was what made this a soap opera. Nobody except Joe Weber saw coincident events when you ran two bar detectors. And the accusations went back and forth. Joe said, well, obviously you must have screwed it up because mine works and yours doesn't. And that went through several iterations, through several international conferences. But if you read the transcript of the GR7 meeting in Tel Aviv in 1974, you can see that to everyone except Joe Weber, his claims were dead. No one had been able to see the same thing as Joe. And what's the reason? We don't know. Okay. Now, here is the hindsight statement that it couldn't have been right. We now know, but it took real work by real people. Very excited about what they were doing to show that in the day. Now, I want to pick up another thread from the Chapel Hill Conference of 1957, and this is the thread that led in a much more direct way to the creation of the current generation of interferometers. And the person I want to focus on to follow this thread is Ray Weiss, my postdoctoral supervisor, who was too young to have been invited to the Chapel Hill Conference in 1957. He was just a grad student. Something I just learned about the history of the Chapel Hill Conference. It was one of the very first international relativity meetings, but it was the first one to which junior people, that is to say postdocs and junior faculty, were invited. There had been in 1955 a 50th anniversary of Special Relativity Conference, and all the young people in relativity were pissed off because no young people were invited. So part of what made the Chapel Hill Conference work is there was already a ferment in the field saying, come on, it's not just for old people. Let's do it. But Ray was not there. He was a graduate student working on a dissertation on atomic beams with Gerald Zacharias as his supervisor. Now, it wasn't just atomic beams. It was actually to try to invent a quiet enough atomic clock so that one could measure the gravitational redshift. That was what Zach had tempted Ray with. So they were hard at work on that. This was before the gravitational redshift was measured by Bob Pound at Harvard a few years before. So Ray was becoming a great experimental physicist at the time, and he kept his interest in making measurements to test relativity, and he nurtured that by doing a postdoc with Bob Dickey at Princeton in the early 60s, and that both nurtured his interest in gravitation and also improved his experimental chops, because Dickey was both a great relativity theorist and one of the great experimental physicists of the 20th century. So that was great background for Ray. But he didn't really start thinking in particular about the gravitational wave problem until he came back from his postdoc. He was a junior faculty member at MIT, and his department chair said, "Oh, Weiss, you're interested in relativity. Teach our relativity course." And Ray had actually never taken a relativity course. So he said, "Oh yeah, yes sir, of course, I'll do that." And then ran back to his office. I gotta learn this relativity stuff, all the theory that I never got. And so he's rushing like crazy to stay one lecture ahead of the students. And he tried to figure out for himself, so that he could teach it, all right, what of all this mathematics represents actual measurable effects and what of it is just mathematics, right? The same thing that bedeviled everyone through, including Einstein. And he came across, by virtue of having read Weber's papers, where he was always very good to say, the basic idea that I got for this comes from this paper by Pirani. And Ray says, great, okay, I'll read the paper by Pirani. And he didn't get a hold of the Chapel Hill transcript, but he did read the 1956 papers that were the basis of Pirani's talk. He said, okay, that's it. Now I see how to find what's measurable. And Ray also saw, by virtue of reading those papers and not reading the Chapel Hill transcript, that when Pirani had first thought the best way to explain how you could do a measurement between these neighboring freely falling masses whose relative motions were governed by the equation of geodesic deviation, Pirani didn't mention either a spring, as he told Bondi he had, or a dashpot, as Bondi had suggested he used for the measurement. Instead, what you find in that paper is Pirani wrote this: it is assumed that an observer, by the use of light signals or otherwise, determine the coordinates of a neighboring particle in his local coordinate system. And Ray was one of the key developers of lasers. And he said, yeah, I know the best light source in the world. Let's implement Pirani's prescription, not by this nutty thing that Joe invented with all the dynamics of this bar and really difficult time coupling energy out of the stretching of the spring. Let's do what Pirani actually proposed, namely do measurements in the classic Einstein train experiment style, exchange light signals between those neighboring particles, and by travel time measurements, see what was the relative motion of free particles. And Ray was developing lasers along with everyone else. This was a great explosion of laser technology in the early 60s. And so he said, okay, I understand this picture, and I'm going to find a way to build some version of this and use lasers, travel time of light from laser beams between pairs of particles, and look for this pattern. And Ray very soon figured out that this was gonna be a lot better, a lot more sensitive than Weber's idea. First of all, he realized you didn't need this diagram. I don't know if Ray ever drew this exact diagram, but it says you don't need a 9x9 grid. Weber showed you only needed 2, but Ray said actually it would be better if you use 3 test particles, because there's this wonderful anti-symmetry between the effect on perpendicular arms. And so you can make the measurement as a comparison between the time it takes to go here and back versus the time it takes to go here and back. And any experienced experimental physicist knows that it's much easier to make comparison measurements precisely than to make absolute measurements. We can talk about that over dinner if that's not obvious. And Ray said, I don't even have to invent an apparatus that compares the travel time between 2 perpendicular paths through space. Michelson invented that apparatus in 1881. So I will make one of my test masses a mirror. I'll make another of my test masses a mirror. These should both be highly reflective. And I'll make the third one at the corner of the L a half-silvered mirror, as we call it, a beam splitter. And I'll send laser light towards the beam splitter. Half will be transmitted, half will be reflected. When those 2 beams meet again at the beam splitter, the amount of light that travels in this direction, that consists of the superposition of this reflected beam and this transmitted beam, that will tell me whether the 2 light beams on those perpendicular paths took precisely the same amount of time to go, or whether there was some shift, perhaps an oscillating shift in the travel time difference down those 2 arms. And here is just a reminder of how a Michelson interferometer works in that way. You can set it up, if you want, so that when nothing is happening, the oscillating electric field in the light from the one arm and from the other, from the X arm and the Y arm, you can set it up so that the operating point is that they are in phase in the beam that's traveling towards your photodetector down here. If so, then in that state, there's constructive interference. We're doing an interferometer, and that interference state is light adds to light and gives you more light. Or, if that were your operating point, say, a gravitational wave could disturb that. And then they wouldn't arrive in phase, and the light would be less bright. Or maybe even you can get destructive interference, and then you would see no light. So what you've got in a Michelson interferometer is a mechanism that I like to call a transducer from arm length difference in perpendicular directions to brightness. And brightness is something we know how to measure. Put a silicon photodiode in that beam and you can get out an electric current that tells you how bright that is. So for technical reasons, we actually choose this as our operating point. We like to set it up. I think I will have an opportunity to explain why that is later. If you were merely a good and not a brilliant experimental physicist, any good experimental physicist would choose the midpoint for reasons that I hope are obvious, but if not, I will gladly talk about them over dinner. But it turns out there's a good reason to work with that operating point, even though it seems obviously nutty. But let's let that go for a moment and take the takeaway that a Michelson interferometer is precisely the kind of apparatus that takes potentially very broadly, widely separated objects and allows you to make a measurement at one spot with electronics that we understand that is proportional to the difference in arm length and can in principle measure it with great fidelity. And here is another poorly published key document of the field. The original poorly published key document is the Chapel Hill Conference Proceedings, although Pirani, bless his heart, actually wrote papers and sent them to a journal. Ray, when he wrote down the idea for implementing gravitational wave detectors with Michelson interferometers illuminated by lasers and with the arm lengths measured in kilometers, he never sent that to the Physical Review or the Gravitational Research Foundation essay contest or anything. He submitted it to a quarterly progress report of the lab at MIT that gave him office space. It says, here, I've been doing something, okay? And that's all he did with it. And I'm like, really? But it's not so hard to find copies of this paper, and it did circulate, even though it was very poorly published. And it's amazing. It is a tour de force of planning an experiment. And you can find this now, but you will read this key number. Weber had sensitivity of 10 to the minus 15. Weiss says, here are some more or less reasonable numbers that if you plug them in to the noise model of this kind of apparatus, you could reach a sensitivity of 10 to the minus 21, which we now know with the benefit of hindsight is what it took. Actually, we need a little bit more because the amplitude of the waves is 10 to the minus 21, and this would have been the size of the noise. So it needed to be a little better. Here is one of the several URLs at which you can find a copy of this quarterly progress report for the Research Lab of Electronics. And the most amazing thing and the most important reason to read it is to see how, at his desk in 1972, Ray Weiss could write down almost the entire list of problems that needed to be solved, of noise terms that would contribute to the noise budget. There's only one or two important important noise terms that don't appear there, and not just as a bulleted list like on one PowerPoint slide. He made numbers for all of them, and the numbers were not bad at all. So you see a great experimental physicist at work, and you see the birth of the interferometric gravitational wave detection program precisely there. Now, we have 20 minutes before the party, right? So let's go as far as we can in understanding how this works in just a little more detail. And what I'd like to do is play for you maybe several times to get everything out of this, an animation put together by graphic designers at Caltech after the discovery was made. Before I click go on this, let's see that this is a perspective view of a Michelson interferometer, mirror here, mirror there, beam splitting mirror, laser, screen that we can pretend is a photodetector, but that we'll look at as a screen as the graphic artists let us look at it. And when I first press go, we're going to see light from the laser illuminate, fill this interferometer, go down the arms and back, and then we're going to look at the state of the light beam coming out of this port of the beam splitter towards this screen and see how it depends on the length difference between those two perpendicular arms. So that's what we're looking for. Oops. Okay, light is filling the arms, it's coming back, and now look, the operating point was chosen to be dark, but as the arm length difference oscillates, we see an oscillating brightness. So now we're going to slow it down a bit, and we're going to be reminded in one of the worst not to scale drawings ever drawn in the history of scientific visualization that we've got two beams whose phases matter, and we've set it up to have them be in antiphase. So we've created a dark port there, but now as the arm lengths shift in antiphase, because that's what the gravitational wave will do, the phase goes from being destructive to a different phase relationship, and the brightness changes there, and that's the way you see a gravitational wave. Except, let's critique it just a tiny bit. That's the basic idea, and the basic idea is correct, except, oh my goodness, not only is the wavelength of the light horribly wrong, but the size of the gravitational wave is horribly wrong. So it's not this easy. But also, notice that there's a real problem with operating at precisely the dark port. If you're literally at the dark port and one arm lengthens, the other shrinks, the dark port gets brighter. But if the opposite happens, it also gets brighter. So you have given up in this version of the apparatus on the chance to make a faithful linear record. You've squared it, and who wants to do that if you're trying to measure something? So there's a lot of details. We know this. Okay, that's not quite how we operate it, but just so you know that it's actually a little more subtle than that, I'll explain how you get around the squaring. All you need to do is not operate at precisely the dark port, just a little bit to one side, then knowing that your arm lengths are not going to change by much at all, you recover a linear effect. It gets brighter when one arm is longer and dimmer when that arm gets shorter. So this is just a visualization problem. It's not something real wrong in the apparatus. But this represents, in cartoon version at least, a mechanization of Pirani's injunction that what you ought to do is measure the relative accelerations of pairs of particles if you want to see what's physical in a gravitational wave or any other relativistic phenomenon. So we'll have a lot more to say about real interferometers in our time together, but let's say something else about what is so cool about being able to detect gravitational waves, especially with an apparatus like this, which, if you just offset it a bit from the dark port, is actually giving you a faithful time record of the arm length differences. That's important because gravitational waves have a property that in principle electromagnetic waves have, but in practice electromagnetic waves, at least from astronomical sources, never have. What I'm referring to is that if we measure the strain as a function of time, okay, that arm gets that big for a while and then it oscillates and now it's shorter and it's longer, and that's happening at this rate, and we make a graph of h of t, that tells us just through a few scalars it is proportional to the time history of the second time derivative of the mass quadrupole moment of whatever object generated the gravitational waves. Now I'm going to be saying precious little to none about gravitational wave sources other than what I'll say in the next few slides, but we have a whole set of lectures, right, on gravitational wave sources. So you will learn as much as you wanted to know, I hope, about why this is the source term. But let me point this out. Gravitational waves are generated by, when we can detect them, by the coherent motions of just a couple of masses. Our prototype signal always was, and now it has become, you know, our banner. Two stars, two massive objects in orbit around each other. It's a very simple calculation to figure out what is the second time derivative of the mass quadrupole moment of two objects in orbit around each other. And not only can we calculate that from moment to moment, but it's not too hard to calculate the time history of what you expect as that system evolves. And it evolves, remember, because all the Newtonian mechanics you learned in your first few years of university are wrong. Orbits aren't stable. They evolve because they shed gravitational waves which carry energy away, and therefore every orbit must evolve, but we can calculate the evolution of the orbit of a binary system. And if we can measure the time history of the gravitational wave signal, that is up to these constants of proportionality. Finally the rain. Telling us the time history of the second time derivative of the quadrupole moment. That is to say, we can read the story that is being brought to us by the gravitational wave signal and interpret it in a very direct way. Now, in principle, electromagnetism works the same way. I could have two charged objects moving with respect to each other, or even just one, and if that was what was making my light signal or my radio signal, I could do the same. But almost every astronomical source of electromagnetic radiation is actually the incoherent superposition of the accelerated motion of many charges, and therefore this line of obvious interpretation is closed to us. But for all of the difficulties of gravitational wave detection, and there are legion, once you succeed, you have this fabulous benefit that the signal will tell its story. There was no doubt whatsoever that GW 150914 was the gravitational wave that came from a 36 solar mass black hole orbiting a 29 solar mass black hole. It had to be because of the functional form of h of t. Now, I said, it's just some constants, but let's think about those constants. R is measured in megaparsecs or gigaparsecs. That's not so good, it's in the denominator. G's in the numerator, that's kind of a small coupling constant. C to the fourth in the denominator, really? That's why when you say, okay, I've got this black hole and this black hole, and there's a huge amount of mass, and they're moving really fast, we still end up with maximum detectable strains at a detector on Earth of only 10 to the minus 21. This factor can be big, but this is really small. but it does tell its story. And every signal that comes from a binary system will have some version of this basic pattern. For a while, you can fool yourself into thinking you're looking at a sinusoid, but if you look for a while, you notice that its frequency is rising and its amplitude is getting stronger, and then something happens and then dies away. The two stars crash into each other. And this is a slightly confusing graphic in that we've got two time series but with two different time scales. Here's a long time scale, so you see a lot of the pattern, and then here's a zoom into the last few cycles, and this looks more like we actually were able to detect. In fact, our first signal just kind of looked at that part. But whenever you see that pattern, you know that the source was a binary system. And then from the details, how fast did it sweep up? That tells you about the mass scale. And how fast did the sweep rate change? That tells you about the mass ratio. And there's all sorts of physics you can learn from the ring down part. And I will leave the details of that to what you'll learn on gravitational wave sources later in the school. But there's something else that's amazingly cool. For actual sensible astrophysical sources of gravitational waves, that is, binaries where, for obvious or not so obvious reasons, the masses are measured in solar masses, it turns out that the signal eventually sweeps up into the band of human hearing. Who ordered that? That's just amazing. And so you can train your ear, actually, to tell the mass of the binary system that you detect. So first of all, let's play what you get from 10 solar masses on 10 solar masses. Oops, that was not supposed to happen. Let's try again. Okay. Could you hear that it ended at a higher frequency than it started? But it didn't end at a really high frequency. The two black holes crashed into each other before their orbits were so fast that you went up to like the top end of the musical scale, but you could hear it. Now, let's see if we can listen to 1.4 and 1.4 solar masses. Can you hear that? This is really slow. Why is it really slow? It's only 1.4 solar mass and 1.4 solar mass, and the luminosity, well, the orbit is slow. We started really low, but it's not evolving very quickly because it's not very luminous. Let's see if I can skip ahead. All right. Oh, we're going to get up there. Okay. Qualitatively the same in that you hear a sweep up in frequency and in loudness, but easily distinguishable. Anyone could tell the difference between a binary neutron star and a binary black hole. The story is there in the detected signal. Yes?
So I already have this, but I'm curious if there is a similar version of the noise of the detector.
We'll hear it in the noise in just a moment. Okay? Right, because, thank you very much, right? That made it seem easy, right? Let's just turn on our detector and we're sure to hear it, right? That was really audible when it was in the right frequency range, but it's anything but that because the signals are so weak that they are, in fact, drowning in noise. And probably most people in this room have heard this, but I'll play it again. Give me a moment though, let me just remind you all that what I'm about to play is 8 versions of the first detected signal, GW150914, twice at as faithful a reproduction as we can do it, twice upshifted by 400 hertz to make the pattern more audible because the actual signal only made it up to about 250 hertz. And that's kind of low. Then you'll hear it again at baseband without the upshift, and then twice more with the upshift. And this is in detector noise. Now there's been some filtering to make it sound a little bit easier to hear, but not very tricky filtering. So twice unshifted, twice shifted up, twice unshifted, twice shifted up. You can hear it. You can know that's not a neutron star. It's not a binary neutron star collision because it ended at a really low frequency. And it was all over in 0.2 of a second. Now, you can also tell that it was freaking loud, right? Because, you know, okay, we cut out the frequency bands where it had no, where the signal was not strong. So it's not that we were listening to the full possible band of sensitivity that LIGO presented, okay? That's just being simply craftsmanlike, all right? But nobody guaranteed us that, okay, you turn on advanced LIGO when it's still a factor of 3 before its design sensitivity, and something that easy to detect will come through. So that was a tremendous gift that no one was expecting. So before we move on from this listening, let me point out a few other features of this animation that I'm sure many of you have seen. It shows data both from the LIGO Hanford interferometer in Washington State and the LIGO Livingston interferometer in Louisiana. And it shows filtered versions of the time series. If we plotted this at full bandwidth, you couldn't see it buried in the high frequency noise, but you make a low pass filter and darn, that looks like a binary. You see the last couple of orbits, you see the coalescence, and then we've wasted person years on the question, how much of the ring down should you say you're seeing? We can talk about that more later, but other people are more expert than me. Let me just point out something else that will come in handy later. In addition to the filtered time series representation of the data, superposed on this is a time frequency graph of the kind called the spectrogram. And at a later meeting, I'll have a lot more to say about what it means to go from a signal that's a function of time and present its frequency content. But for now, let me just use the fact that I think most people in this room have heard of Fourier transforms. And so imagine that you do this operation. Chop the time series into short bits, Fourier transform each little bit, square, take the norm squared of that Fourier transform so you just see the power at each frequency, and you're not trying to say, is it a sine or a cosine? And then do that over and over again for one time slice after another and make a heat map plot of how strong at which frequencies do you see the oscillations in that squared Fourier transform version. And you see that this sweeping up, what I think I said was sweeping upwards in frequency, indeed shows up as this characteristic upward sloping and arcing upward because the rate of frequency evolution is speeding up. And you can also see in this time frequency representation what is easy to see in the pure time domain representation, namely that it's louder at the end than at earlier times. So often it's more convenient to make these kinds of plots if for no other reason than this kind of math operation does the filtering for you and lets you see, oh yeah, I only needed to pay attention to this range of frequencies. Most times you would make a time domain plot, you'd have to, after the fact, do the filtering. So this does it for you. It's got other advantages too, but we'll let it go. And let's see if we have time to do anything else. No, that is a great stopping point. So we'll pick up tomorrow afternoon with more about gravitational waves. Anyway, thanks for your attention.
So, well, I can't remember. Was signal to noise
when we pulled out all of our tricks, 25 or so.
If I were to look on this curve and say, what is the noise I'm seeing in that signal, can I sense the little ripples I'm seeing or not?
It's even a little better than what you see there, because the calculation that you do to get 25 coherently adds up all the cycles according to the pattern that's buried in there. So if you actually said, now how big are those little ripples and how big is the tallest thing, you wouldn't get 25. But that's a trick I'll explain later that we've known. Okay, we're about to be offered drinks. I'll happily take questions there, but let's not keep us all from the welcome party. So see you all over there.